Men have always been fascinated by the sun, moon and stars. Even our remote cave-dwelling ancestors must have looked up into the sky and wondered at what they saw there. Were the sun and the moon gods, or at least the dwelling places of gods? Today, astronomy has become an exact science. It's the basis of all timekeeping and navigation, and moreover, it is still one of the very few sciences in which the enthusiastic amateur can still make really important contributions. Many people believe that to take a real interest in astronomy, you need to spend a vast sum of money on a large telescope. I can assure you that this is not true. You don't need a big telescope, or even a telescope at all. There's a tremendous amount to be seen with the naked eye. The next step is, in my view, to use a pair of binoculars. They'll show you a great deal. But eventually, you may think about a telescope. And this is the first one I had when I was 10. That was in 1933. And this is how it works. The light from the object you're looking at goes through this glass lens known as an object glass. Actually, it's a compound lens, but no matter. The light rays are bunched up and brought to a focus, and the image is enlarged by a second lens known as an eyepiece. Note that it's the eyepiece which does all the magnification. The role of the object glass is to collect the light in the first place, and the bigger the object glass, the more light you can collect. This telescope has an object glass 3 inches across, and in my view, it's the minimum useful size. Rather than get a smaller telescope, go for binoculars. Now this is a different kind of telescope, a reflector. Here, the light passes down an open tube and hits a curved mirror. The mirror sends the light back up the tube onto a smaller, flat mirror. This sends the rays into the side of the tube when an image is formed and enlarged by an eyepiece as before. This telescope has a 6-inch mirror, and it's about the smallest, which is really useful. Inch for inch, a lens is more effective than a mirror. But today, we have vast telescopes. First, let's get the basic facts straight. The Earth on which we live is a planet, a globe over 4.5 thousand million years old and almost 8,000 miles in diameter. It moves at something like 66,000 mph around the Sun, which is a star. This may surprise some people. The Sun is a perfectly ordinary star, and it appears so much larger and hotter than the other stars only because it's so much closer to us. The distance between the Earth and the Sun is approximately 93 million miles. Now that may sound a long way. By normal standards it is, but it isn't far to an astronomer. In astronomy, we have to get used to immense distances and vast spans of time. Nobody can really appreciate them. I certainly can't, but we just have to accept them. The stars are so far away that they look like points of light, and we can't see them in the daytime simply because the sky is too bright. To show you how far away they are, let me give you a scale model. We will represent the Earth-Sun distance by 1 inch. So where must we put the nearest star? Over 4 miles away. No wonder that the stars look so much feebler than the Sun, even though some of them are much more powerful. The Earth isn't the only planet. There are 8 others, all moving around the Sun at different distances and in different periods.
I think that's an interesting thing.
This one piece will make 52 layers.
Watch on mobile devices or the big screen. All for free. No subscription required.
The Sun's family, or solar system, is divided into two well-marked parts. First we have four small, solid planets: Mercury, Venus, the Earth and Mars. Then comes a wide gap, in which move thousands of dwarf worlds which we call minor planets or asteroids. Then come four giant planets: Jupiter, Saturn, Uranus and Neptune, and one odd little world, Pluto, which doesn't fit into the general scheme and may not really be a proper planet at all. The planets look like stars with the naked eye, and some of them are brilliant, but they have no light of their own, and shine only because they're reflecting the rays of the sun. This is also true of the moon, which really does go round the Earth and is much the closest natural body in the sky. We have only one moon, but other planets have more. Saturn has as many as 18. The stars aren't really fixed in space, but they don't seem to move much over periods of many lifetimes compared with each other. Not so with the planets, which are much closer to us. They seem to shift slowly against a starry background from one night to another, and this is how the ancients first realized that they were different from stars. The rule is the further, the slower, and the stars are so far away that, relative to each other, they hardly seem to move at all. Of course, the whole sky moves round from east to west, but this is only because the Earth is spinning on its axis from west to east. We are observing from a moving platform, so to speak. The Earth spins on its axis in roughly 24 hours. Northward, the axis points to the north pole of the sky, marked fairly closely by a brightish star, the pole star. This means that the pole star hardly moves at all, and everything else turns around it. If you take a camera at night, point upwards at the pole star, and give a time exposure, you will get this effect. As the stars move, they leave their trails. If you go to the North Pole, you'll see the pole star vertically overhead. Go south of the equator, and you won't see the pole star at all, because it will stay below the horizon, and there isn't a bright south polar star. Just as the sun is king of day, so the moon is queen of night. And the moon really is near. Its mean distance from us is less than 250,000 miles. Fly 10 times round the Earth, and you will cover a distance greater than that between the Earth and the moon. It takes just over 27 days to complete one circuit, and of course it shows phases or apparent changes of shape from new to full. When it's almost between the sun and the Earth, its dark or night side is turned towards us, and we can't see the moon at all. This is the true new moon. As it moves along, we start to see a little of the day side. The moon becomes a crescent, then a half, and then, when it's on the far side of the Earth with respect to the sun, full. After that, the phases are repeated in reverse order, and we have the next new moon. When the full moon passes into the shadow cast by the Earth, its supply of direct sunlight is cut off, and we have an eclipse of the moon. The moon doesn't, usually, vanish completely, because some of the sun's rays are bent onto it by way of the shell of atmosphere surrounding the Earth. But the moon turns a dim, often coppery colour, until it passes out of the shadow again. Eclipses don't happen every month, because the moon's orbit is tilted, and on most occasions it escapes eclipse. I've said that the moon is much smaller than the Earth, and it has less mass. If you could put the Earth in one pan of a gigantic pair of scales, you'd need 81 moons to balance it. This means that the moon doesn't pull so strongly as the Earth. Its gravity is weaker, and this has one very important effect. The moon has no air. The air which we're breathing on Earth is made up of untold millions of tiny particles of air, all flying around at high speeds. If a particle could travel outward at 7 miles per second, it would escape the pull of our gravity. Fortunately, our air particles can't travel as fast as that. But on the moon, escape velocity is only 1.5 miles per second, and that's not enough to hold the air around the moon. Any air the moon may once have had has long since leaked away into space. Today, there's no atmosphere there, and therefore no water and no life. All the surface details are sharp and clear-cut. No mist, no cloud, no rain, no weather. Even with the naked eye, we can see details on the moon. Broad, dark plains, which we still miscall seas, even though there's never been any water in them. We still use romantic names. The Sea of Serenity, the Ocean of Storms, the Bay of Rainbows, and so on, because it was once believed that they were true seas. There are high mountains, often named after Earth mountains, but the whole lunar scene is dominated by the craters, which are everywhere. Some of them are well over 100 miles across. You can see these with any telescope or good binoculars. But the appearance changes very markedly from night to night. Remember, the moon shines only by reflected sunlight. When the sun's rays are coming straight down and there are almost no shadows at all, it may be difficult to identify the craters. So full moon is the very worst time to start looking at it through a telescope. The Earth spins round once in 24 hours, but the moon takes just over 27 days. If you're on the moon, a lunar day is almost as long as 2 Earth weeks. And the moon's rotation period is exactly the same length as the time taken for the moon to go once round the Earth. This means that the moon keeps the same face turned towards us all the time, and there's part of the moon that we can never see from Earth. The idea of travel to the moon is very old, but of course no ordinary flying machine can take us there. An aircraft can't work unless there's air around it, and there's no air between the Earth and the moon. Our atmosphere doesn't extend upward for more than a few hundreds of miles, and the moon is almost 250,000 miles away. The only answer is to use a rocket, which works by what Isaac Newton called the principle of reaction. Every action has an equal and opposite reaction. Consider a firework rocket. It's made up of a hollow tube filled with gunpowder. When you light the blue touch paper and retard immediately, the powder starts to burn. It gives off hot gas. This gas rushes out of the rocket's exhaust, and as it does so, it kicks the rocket in the opposite direction. The first unmanned rockets to reach the moon were Russian. They were sent up in 1959, and one of them went right round the moon, sending back pictures of the far side, which we can never see from the Earth. As we expected, the far side proved to be just as crater-scarred and just as barren as the side we've always known. In 1969, the first men went to the moon. The spacecraft Apollo 11 carried 3 men: Neil Armstrong, Buzz Aldrin, and Michael Collins.
Eagle, you're looking great. That's 40 feet down, 2.5. Picking up some dust. Houston, Tranquility Base here. The Eagle has landed. I'm going to step off the limb now. That's one small step for man, one giant leap for mankind.
They found a strange place. Aldrin described the scene as magnificent desolation. There was no sign of life, either past or present. the moon has always been sterile. On the moon, a man has only 1/6 as much weight as he does at home, so everything seems to happen in slow motion. Other missions followed, the last one in 1972. By now, we have a good knowledge of the moon. It's about the same age as the Earth, around 4.5 thousand million years, and most astronomers believe that the craters were produced long ago when the moon was hit by solid bodies from space, but almost nothing happens there now. Yet before long, we should be able to set up a proper lunar base. This must certainly happen during the 21st century, and I'm very ready to believe that some of you, now watching this video, will be able to go there. Meanwhile, do take a telescope or binoculars and look at the moon's mountains, craters, and waterless seas. But I think it's time to start our journey, and where better than the Sun, the centre of our solar system. One thing you must not do is to look directly at the Sun through any telescope or binoculars. It isn't even safe to stare at it directly with the naked eye. It's very hot indeed. Even the surface temperature is not far short of 6,000 degrees centigrade, and it's also very large. Its diameter is 865,000 miles. That's more than 100 times greater than that of the Earth. And you could pack 1 million globes, the volume of the Earth, inside the Sun and still leave room to spare. If you focus the Sun's light and heat onto your eye, you will blind yourself permanently. The trap is that some small telescopes are sold with dark sun caps, and it's said that it's safe to put the sun cap over the eyepiece and then look direct. Believe me, it isn't. No dark cap can give proper protection. It's always apt to shatter without warning, and a second's exposure will be tragic. There's only one rule for looking straight at the Sun: don't. However, there is one way. Point the telescope at the Sun without putting your eye anywhere near the eyepiece, and project the Sun's image onto a screen held or fastened behind the eye end. You will see the Sun's disk well, and you may see dark patches known as sunspots. These spots aren't really black. They look dark only because they are around 2,000 degrees cooler than the surrounding surface. You can't always see them. Every 11 years or so, the magnetic activity which causes spots on the Sun is very active, and there may be many groups of spots. At other times, as in the mid-1990s, the Sun is quieter, and there may be many spotless days. The Sun takes several weeks to spin on its axis, and so if you plot the spots from day to day, you will see them being carried across the Sun's face. It's always worth doing, and of course you can do that in the daytime. We say that the Sun is burning, but it isn't burning in the same way as a coal fire. The Sun shines because of what we call nuclear transformations going on inside it, near the centre of the globe, where the temperature is at least 14 million degrees, probably rather more, and the pressure is colossal. Over 70% of the Sun is made up of hydrogen. Near the core, strange things are happening. The bits of hydrogen are running together to build up bits of a heavier gas called helium. And each time this happens, a little energy is set free, and a little mass, or weight if you like, is lost. It's this energy that keeps the Sun shining, and the mass loss amounts to 4 million tons per second. Imagine the weight of 4 million coal trucks. But please don't be alarmed. The Sun is so huge that it won't change much for several thousands of millions of years yet. Most of what we know about the Sun had been learnt by using instruments based on the principle of the spectroscope. What we usually call white light isn't really white at all. It's made up of a combination of all the colours of the rainbow, from the red to orange, yellow, green and blue to violet. If you pass a beam of sunlight through a glass prism, you will split it up into a coloured band. Crossing this band are dark lines. Each dark line is due to one particular substance, and so we can tell what the sun's made of. When the Earth, the Moon and the Sun are exactly lined up, the Moon will blot the Sun out for a few minutes, causing what we call a total solar eclipse. The Moon is a small world, only just over 2,000 miles across, so it's much smaller than the Earth. Its diameter is only 1/400th that of the Sun, but is 400 times nearer, and by sheer luck the two bodies appear the same size in the sky, or nearly so. When this happens, we can see the Sun's outer atmosphere, and the sight is magnificent. Round the Sun's edge can often be seen masses of red hydrogen, which we call prominences, and beyond these comes the glorious pearly corona, which spreads out in all directions. If you have the chance to see a total eclipse, don't miss it. The problem is that the Moon's shadow is only just long enough to reach the Earth, so that you have to be in just the right place at just the right time. We always know when eclipses are going to happen. The last total eclipse visible in England was in 1927. The next will be on the 11th of August, 1999. Using spectroscopic equipment, we can now see the prominences at any time, and we can take films of their motions. They can shift very rapidly indeed. But this does need special equipment, and again I say, be careful. I don't apologize for stressing this, because it is so important. You have only one pair of eyes. Of course, the Sun is the ruler of the solar system. So let's remind ourselves of his family and take brief looks at them one by one. 4 small planets, Mercury to Mars. A wide gap filled by the midget asteroids, and then the 4 giants. We come first to Mercury, which many people have probably never seen. It's small, only 3,000 miles across, closer in size to the Moon and the Earth, and quite a long way away. On average, it's a mere 36 million miles from the Sun, and it speeds round in a mere 88 days. The problem is that it's always in the same part of the sky as the Sun, so with the naked eye you can see it only when it's at its best, either low in the west after sunset, or low in the east before dawn. Look for it by all means, but don't sweep around with binoculars unless the Sun is completely below the horizon. You might look at the Sun by mistake. Because Mercury is closer to the Sun than we are, it shows phases similar to those of the Moon, and for much the same reason, bearing in mind that Mercury goes round the Sun, not round the Earth. When full, it's on the far side of the Sun, so it won't be visible. Very occasionally, when new, it may pass in front of the Sun and show up as a black spot. This is called a transit. The next time this happens will be in 1999. Because Mercury is small and lightweight, it has very little atmosphere. One spacecraft has passed by it, Mariner 10, in 1973 and 1974, and sent back pictures showing a rocky, cratered landscape, very like that of the Moon. Of course, it's hot. The surface temperature rises to hundreds of degrees, but the nights are bitter, and the nights on Mercury are very long because the planet is a slow spinner. I can't imagine that anyone will go there in the foreseeable future. If they could, they'd find a barren, scorching landscape under a black sky. Still, it's worth looking for Mercury just for the fun of finding it, and yearly almanacs will tell you when and where to look. Planet number 2, Venus, is as different from Mercury as it could possibly be, and you can't mistake it, because it is so very brilliant. Like Mercury, it shows up in the west after sunset, or the east before sunrise, but it looks almost like a small lamp, and it can even cast shadows. This is partly because it's bigger than Mercury, almost exactly the same size as the Earth, and partly because it's nearer. At its closest, it's only about 100 times as far away as the Moon, and of course, it shows phases from new to full. It doesn't often pass in transit across the Sun's face. It last did so in 1882, and it won't do so again till 2004, so there can be nobody now living who's ever seen a transit of Venus. But though Venus and the Earth are near twins, they are non-identical twins. Look at Venus through a telescope, and all you'll see will be the top of a layer of cloud. But you can't see through those clouds. There's no such thing as a clear day on Venus, and the atmosphere is different from ours. It's made up chiefly of the heavy gas carbon dioxide, and those shining clouds are rich in sulfuric acid. Add the fact that the surface temperature is nearly 1,000 degrees Fahrenheit, and the pressure is at least 90 times that of our air at sea level, and you'll realize that Venus is not a very pleasant place. The Russians have landed automatic probes there and sent back pictures of the surface, but our best maps have been made by using radar-carrying spacecraft, of which the latest was Magellan. Magellan has shown us huge volcanoes, which may well be active. We'd even go for a simulated ride over Venus. Look at this towering peak. But I'm quite sure that nobody will go there in our time. Venus is odd in many ways. It spins very slowly the wrong way. So from Venus, the Sun rises in the west and sets in the east 118 Earth days later, giving a full rotation period of 243 days. This is longer than Venus's old year of nearly 225 Earth days. All in all, the differences seem to stem from the fact that Venus is over 20 million miles closer to the Sun than we are. It may have had seas once, but they've long since evaporated. We come next to Mars, the red planet. It really is red, which is why it was named after the god of war. It is smaller than the Earth, but larger than the Moon. It takes 687 Earth days to go around the Sun, and its own day is just over half an hour longer than ours. Telescopes show a red disk with white ice caps at the poles, and dark markings which were once thought to be seas, but are now known to be areas where the red, dusty stuff had been blown away by winds in the thin Martian atmosphere, exposing the darker surface below. Years ago, astronomers believed they could see streaks on Mars which were taken to be canals built by the Martians, whatever they might be, in a vast irrigation system. But, alas, the canals don't exist. They were simply tricks of the eye. Spacecraft have flown past Mars and sent back pictures showing craters, plains, valleys, and huge volcanoes, one of which, Olympus Mons, is 3 times the height of our Everest and is crowned by a 40-mile crater. In the 1970s, Viking spacecraft made controlled landings there, mainly to search for any signs of life. They didn't find any, and it now seems that there's no living thing on Mars, mainly perhaps because the atmosphere is so thin and is made up of carbon dioxide. Using the Viking results, we can at least go on a trip over the Martian surface, and it's going to be spectacular by any standards. In the 21st century, I'm sure we'll set up manned bases there. But one thing we can never do is to go out into the open unprotected by space equipment. We can never turn Mars into a second Earth. Mars has two moons. They're called Phobos and Deimos. Both are very small, less than 30 miles across for Phobos, even less for Deimos, and they wouldn't be of much use in lighting up the dark Martian nights. Probably they are not genuine moons at all, but are asteroids captured from the swarm which lies beyond Mars. These asteroids are curious little worlds. We now believe that they are debris left over, so to speak, when the main planets were formed from a cloud of dust and gas surrounding the young sun. Next, the giants, beginning with Jupiter, which is almost 90,000 miles across, but it isn't solid and rocky. Use a telescope, and you will see that it has a yellowish, flattened disk crossed by streaks which we call cloud belts. The surface is made up of gas, mainly hydrogen, and is very cold. Deep inside the globe, there's almost certainly a hot core, surrounded by layers of liquid hydrogen beneath the clouds which we can see. Though Jupiter takes nearly 12 years to go once round the Sun, it spins on its axis in less than 10 hours, and this is why it's flattened. Centrifugal force makes the equator bulge out. Through any small telescope, Jupiter is a fine sight. You may even see the Great Red Spot, which is a whirling storm with a surface area greater than the Earth's. We've sent spacecraft to Jupiter, and the two Voyagers, which bypassed the planet in 1979, sent back superb views. They also told us that Jupiter is a dangerous world. It's surrounded by zones of deadly radiation, which would instantly kill any astronaut foolish enough to venture too close. There's also a very strong magnetic field, and the surface is in a state of constant turmoil with thunder and lightning. No, we'll never go to Jupiter. But Jupiter isn't alone. It has 4 large moons: Io, Europa, Ganymede, and Callisto. 3 of these are larger than our moon, and Ganymede's actually larger than the planet Mercury. You can see them with any small telescope, or even really good binoculars, and there's never any problem in finding Jupiter because it is so brilliant, brighter than any other star or planet apart from Venus. Of the satellites, Ganymede and Callisto are cratered and icy. Io has a red surface with active volcanoes. Since Io also moves inside Jupiter's lethal radiation zones, it must be just about the deadliest world in the entire solar system. Beyond Jupiter lies Saturn, second of the giant planets, smaller than Jupiter, but still much larger than the Earth. Its diameter is over 70,000 miles, over 9 times that of the Earth. Its makeup is not unlike Jupiter's, but is distinguished by its set of icy rings. To me, Saturn is the loveliest object in the sky, and when the rings are well placed, a small telescope shows them well. However, though they measure almost 170,000 miles from end to end, they are less than a mile thick, and when they lie edgewise onto us, and in 1995, they almost vanish. The rings look solid, but they aren't. Saturn's powerful gravity will quickly pull any solid or liquid ring to pieces. The rings are made up of tiny pieces of ice, all spinning round Saturn like tiny moons. In 1980 and 1981, the two Voyager spacecraft gave superb views of them. They are made up of many hundreds of ringlets and narrow divisions. All the giant planets have rings, but only Saturn's are bright. Saturn takes almost 30 years to go around the Sun at a mean distance of 886 million miles, so it takes a spacecraft a long time to get there. But there are also the satellites, at least 18 in all, but only one of them, Titan, is large. You can see it as a star-like point in a small telescope. The Voyager pictures show the top of a layer of orange smog. Titan has a thick atmosphere, but we couldn't breathe it, and the temperature is very low. There are two more giant planets beyond Saturn, Uranus and Neptune, and both have been passed by the same spacecraft, Voyager 2, which was launched from Cape Canaveral in 1977. By sheer luck, at the end of the 1970s, the four giant planets were strung out in a curved line, so that Voyager 2 could pass by them one after the other. Jupiter in 1979, Saturn in 1981, Uranus in 1986, and finally Neptune in 1989, after which Voyager began a never-ending journey out of the solar system. It will never come back, and we're still in radio touch with it, though before long we'll lose contact and we'll never know what eventually happens to it. The outer giants are much smaller than Jupiter or Saturn, but still much larger than the Earth. They too have gaseous surfaces and darkish ring systems. Uranus is rather bland, but Voyager showed dark patches on Neptune, and Neptune's main satellite, Triton, proved to have poles covered with pink nitrogen snow. Triton is so cold that nitrogen, which is gaseous in our air, freezes out. You can just see Uranus with the naked eye, if you know where to look for it. But to see Neptune, you need a telescope. Finally, on the edge of the planetary system, there is Pluto, discovered in 1930 by my old friend Clyde Tombaugh. Pluto looks like a star in ordinary telescopes, but our best instruments can show that it has a companion, Charon. But Pluto's hardly worth ranking as a proper planet, because it is very small, smaller than the Moon. It has a very thin atmosphere and probably an icy surface. It's so far away that it takes 248 years to go around the Sun, but it has a strange path, and when closest in, it's actually nearer than Neptune. Not until 1999 will it again pass beyond Neptune's path. Unfortunately, though, no spacecraft have been anywhere near it. There seem to be large numbers of very small bodies in the far reaches of the solar system, but we also have to remember comets and meteoroids. A comet isn't solid and rocky in the same way as a planet. A typical comet has an icy centre mixed in with rubble, never more than a few miles across. Most comets move around the Sun in long, narrow paths, some of them in periods of a few years, though others take so long that they come near us only once in many lifetimes, and we can't predict them. When a large comet nears the Sun, its ices start to boil off, and the comet's centre is surrounded by a head and often a tail or tails. As the comet moves outward again and cools, the head and the tail disappear, and tails always point more or less away from the sun, so that an outward moving comet travels tail first. A comet is travelling far beyond the Earth's air, and it doesn't move perceptibly against the stars as seen with the naked eye. So if you see something moving quickly, it can't be a comet. It may be an artificial satellite, but if it's very quick, it'll almost certainly be a meteor. Meteors are so small and flimsy that they burn away harmlessly, but now and then the Earth is hit by a larger body, which may strike the ground intact and is then called a meteorite. Note that there's no connection between a meteorite and the shooting star meteor. Meteors are cometary debris, while meteorites almost certainly come from the asteroid belt. We know of many meteorite craters. There's a famous one in Arizona, almost a mile wide, formed when a meteorite hit the desert well over 20,000 years ago. There's always the chance of another major hit, and it could cause great damage. It's even been suggested that this did happen around 65 million years ago, and threw up so much debris that the climate was changed, and the dinosaurs, which had been lords of the world for so long, died out. This may or may not be true, but at least it's a possibility. And we've seen one major impact. In 1994, a comet was observed to hit Jupiter and destroy itself. Up to now, we've been talking about our own local part of the universe, but now it's time to look further afield, to the stars. This is a typical star field. And remember, every star is a sun, and our sun is an ordinary star. I've already said that the stars are very distant, so far away that it would be awkward to measure their distances in miles, just as it would be awkward to give the distance between London and Sydney in inches. Instead, we use a unit called the light year. Light doesn't travel instantaneously. It flashes along at 186,000 miles per second. So in a year, it covers almost 6 million miles, and this is what we call the light year. It takes 1¼ seconds for light to travel to us from the moon, 8.6 minutes from the sun, but over 4 years from the brightest star, Alpha Centauri, in the southern sky. I'm afraid it would take too long for me to give you a tour of the constellations, but believe me, it doesn't take long to learn your way around, because the patterns don't change. My method is to select a few prominent constellations and use these as guides to the rest. When I was a boy, I obtained an outline star map and made a pious resolve to identify one new constellation every clear night. Before long, I had a good working knowledge, and after all, there are only a few thousand stars visible with the naked eye. Of course, the constellation patterns are quite arbitrary, because the stars are at very different distances from us, and the stars in any particular constellation aren't really connected with each other. We are dealing simply with line of sight effects. So let's look now at the life story of a star. It begins by condensing out of a cloud of dust and gas. Gravity makes it shrink. It heats up inside and joins what we call the main sequence, unless it's too small in mass, when it simply shines feebly as a red dwarf before losing all its light and heat. Our sun-like star shines steadily for a long time, thousands of millions of years in the case of our sun, but when it starts to run short of hydrogen fuel, things happen. It starts to use different nuclear reactions, becoming a red giant. When this happens to the sun, the Earth will certainly be destroyed, I'm afraid, but as I said, this won't happen for around 4,000 million years yet. Next, the star throws off its outer layers and becomes what we call a planetary nebula. A bad name. It has nothing to do with the planet and is not a true nebula. The outer layers dissipate. What's left of the star shrinks to become a very small, very dense object called a white dwarf. All its atoms are crushed and broken so that you can pack a ton of white dwarf material into an egg cup. The best known white dwarf is the tiny companion of Sirius, which is as massive as the Sun, but only about 3 times the diameter of the Earth. After a very long period indeed, the the star becomes a cold, dead globe. That's the story of a star such as our Sun. If the original star is much more massive, it'll die more spectacularly. When it runs out of available hydrogen fuel, it collapses. There's an implosion, followed by a rebound, and the star literally blows itself to pieces in what we call a supernova outburst. This doesn't happen often, but in 1987, one of these explosions did happen in the southern system called the Large Cloud of Magellan, and became visible with the naked eye for a time. At its peak, it could match several thousands of millions of suns. And we're left with an expanding gas cloud, inside which is a tiny remnant even denser than a white dwarf. If the original star is more massive still, it can't even explode as a supernova. When the collapse starts, it's so violent and so catastrophic that nothing can stop it. The star shrinks and shrinks, becoming denser and denser and pulling more and more strongly. Finally, it's pulling so strongly that not even light can escape from it. And if light can't do so, then nothing else can, because light is the fastest thing in the universe. The old star has surrounded itself with a forbidden area which can swallow up material, but from which nothing, absolutely nothing, can escape. It has become a black hole. Obviously, we can't see it, and we have to detect it by its effects on objects close to it which we can see. What happened to the old star, I'm afraid I can't tell you, because nobody knows. Unquestionably, black holes are the most bizarre objects in the entire universe. Our star system, or galaxy, contains around 100,000 million stars, of which our Sun is one. It's a flattened system, perhaps 100,000 light years across. The Sun, with its planets, lies almost in the main plane, nearly 30,000 light years from the center of the system. When we look along the main plane of the system, we see many stars in almost the same line of sight, and this produces the appearance of the Milky Way, that lovely band of radiance crossing the night sky. It's made up of stars. The stars look as if they almost touch each other, but this is an illusion. Actually, they're wide apart. We also know that the galaxy is rotating. It takes the Sun about 225 million years to go once round, a period sometimes called the cosmic year. One cosmic year ago, the most advanced creatures on Earth were amphibians. Even the dinosaurs lay in the future. I wonder what the Earth's going to be like one cosmic year hence. But if we could look at the galaxy from above or below, we see that it is a spiral, like a great Catherine wheel. This is no surprise either. Far away in space, we can see other spiral systems, although not all galaxies are spirals. What we do know for certain is that apart from a few comparatively nearby systems in what we call our local group, all the galaxies are receding from us and from each other. Edwin Hubble found that the further away a galaxy is, the faster it's racing away. The expansion is universal, and today we know of systems which are well over 10,000 million light years away and are racing off at over 90% of the speed of light. In fact, galaxies tend to occur in groups, and each group is receding from each other group. We are in no special position in the universe. You can see one problem here. If the rule of the further, the faster holds good, then eventually we'll come to a distance at which an object is moving away at the full speed of light. We'll then be unable to see it at all, and we'll have reached the edge of the observable universe, though not necessarily the boundary of the universe itself, if it has one. It seems that this critical distance is between 15,000 million and 20,000 million light years, but there is considerable uncertainty, and it may even be that there's a major error which may lead to a great deal of rethinking. Everybody wants to know how the universe began and how far it extends. At present, we can't answer either question. According to our present ideas, the universe came into existence at one particular moment in a Big Bang, around 15,000 million years ago, and has been expanding ever since. Whether the universe will finally contract and produce another Big Bang, again, we don't know. And to be candid, neither do we know why or how the Big Bang happened. We must go on trying to find out. So, all in all, There's a great deal that we still don't know, even though we've found out so much in recent years. But to end, let me say again that even if you don't want to save up for a powerful telescope, you can take a real interest in astronomy. Do some reading, get a star map, and learn your way around the night sky. Join an astronomical society, and you'll give yourself a lifelong hobby, as I have myself. I wish you all success and clear skies.